Hi everyone and welcome to this tutorial on CPU scheduling, a core concept in operating systems. Have you ever wondered how your computer decides which task to run first when you're opening multiple programs or running background processes? That's where CPU scheduling comes in. In simple terms, CPU scheduling is the method the operating system uses to determine which process gets to use the CPU and for how long. It's an essential part of processes management that helps ensure efficiency, fairness, and responsiveness in multitasking systems. In this tutorial, we'll walk you through the basics of CPU scheduling, explore common scheduling algorithms like first come first serve or FCFS, and show you how to calculate important metrics like turnaround time, waiting time, and more. Whether you're computer science students or someone curious about how computer manage multiple tasks, this guide will help you understand how CPU scheduling works step by step. So let's get started and take a closer look at why CPU scheduling is so important and how it helps keep your system running smoothly.
What is CPU scheduling? CPU scheduling is the method an operating system uses to decide which process from the ready queue gets access to the CPU. Since only one process can run at a time, especially in single-core systems, scheduling ensures that the system is fair, efficient, and responsive. What is the purpose of CPU scheduling? CPU scheduling affects the performance of the systems by maximizing CPU utilization, minimizing process waiting and turnaround time, and ensuring every process gets its fair share of CPU time. There are two main types of CPU scheduling, preemptive and non-preemptive. Let's break them down. Preemptive scheduling. In preemptive scheduling, the CPU can take control away from currently running process and give it to another. This is useful in time-sharing or real-time system where responsiveness matters. Example of preemptive scheduling algorithms include round-robin, preemptive shortest job first, and preemptive priority scheduling. The advantage and disadvantage of preemptive. Preemptive scheduling is highly responsive and improves CPU usage. However, it's more complex and causes overhead from frequent context switching. In non-preemptive scheduling, once a process starts using the CPU, it runs until it's finished or waits for input or output. The CPU won't switch tasks in the middle. Examples include first come first serve, non-preemptive, shortest job first, and non-preemptive priority scheduling. Advantages and disadvantages of non-preemptive. Non-preemptive scheduling is simple and has no context switching overhead, but it can lead to inefficiencies like the convoy effect, where short processes wait behind long ones. We'll walk through the first come first serve or FCFS scheduling algorithm using a simple set of processes. Let's consider the following processes with their respective arrival times and burst times. In the FCFS scheduling algorithm, the process that arrives first gets executed first, like standing in line at a store. As you can see, there is a Gantt chart there. The Gantt chart shows how these processes will be executed. First, we look at the processes and their arrival times. Since FCFS schedules processes based on who arrived first, we begin with process P1, which arrive at time 0. P1 runs for 5 units of time, so it starts at time 0 and finishes at time 5. By time 5, the processes P2, P3, and P4 have all arrived. According to the order of arrival, process P2 is next. P2 starts at time 5 and runs for 3 units of time, finishing at time 8. Next is process P3, which arrive at time 2. Since it's next in line, it starts at time 8 and runs for 8 units, completing at time 16. And last, process P4, which arrive at time 3, starts at time 16 and runs for 6 units of time, finishing at time 22. Each process was executed in the order of arrival without preemption, and each one waited for the previous to finish before starting. Here are the completion times. P1 finish at time 5, P2 at time 8, P3 at time 16, and P4 at time 22. Next, we'll calculate the turnaround time. You can find the formula at the bottom of the turnaround time column. That's what we'll use to determine each processor's turnaround time. This completion times allows us to calculate the turnaround time for each process using the formula. Completion time minus arrival time equals turnaround time. Applying this, P1's turnaround time is 5 minus 0 equals 5, P2's is 8 minus 1 equals 7, P3's is 16 minus 2 equals 14, and P4's is 22 minus 3 equals 19. This shows how FCFS scheduling handles process execution strictly by arrival time and allows us to compute turnaround time directly from completion and arrival values. Next, we compute the waiting time, which tells us how long each process waited before execution. The formula is turnaround time minus burst time equals waiting time. Applying this, P1's waiting time is 5 minus 5 equals 0, meaning it did not have to wait. P2 waited 7 minus 3 equals 4 units of time. P3 waited 14 minus 8 equals 6 units. And P4 waited 19 minus 6 equals 13 units. This calculation shows how the FCFS scheduling algorithm can lead to longer waiting times of processes that arrive later, especially when earlier processes have longer burst time. In the first come first serve or FCFS scheduling algorithm, turnaround time is the total time a process spends in the system from arrival to completion. To find the average turnaround time, we first calculate the turnaround time for each process using the formula. Completion time minus arrival time equals turnaround time. Based on the given data, the turnaround times are as follows. P1 has 5, P2 has 7, P3 has 14, and P4 has 19. To get the average, we simply add all the turnaround times and divide the sum by the total number of processes. That gives us 5 plus 7 plus 14 plus 19 equals 45. Since we have 4 processes, we divide 45 by 4, which results in average turnaround time of 11.25 units. This value gives us a general idea of how long a process waits in the system from arrival to completion under FCFS scheduling. Next is average waiting time. The waiting time of process refers to how long it waits in the ready queue before it gets executed. We calculate the waiting time for each process using the formula. Turnaround time minus burst time equals waiting time. Based on the given data, the waiting times for each process are as follows. P1 has a waiting time of 0, P2 has 4, P3 has 6, and P4 has 13. To compute the average waiting time, we add all the waiting times together and divide by the number of processes. That gives us 0 plus 4 plus 6 plus 13 equals 23. Since there are 4 processes, we divide 23 by 4, which equals 5.75. This means that on average, each process waited 5.75 units of time before it start executing under the FCFS scheduling algorithm.